In this lecture, we're going to learn about some more things we can do with our requires clause. But before we do that, let's look at the kinds of requirements we can put in our requires clause. The first one is a simple requirement, which is what we have seen so far. We can also do a nested requirement, and we're going to learn about this in a minute. And we can do a compound requirement, which is going to allow us to specify more things about what we require for our concept. There are also type requirements, but these are really advanced for the scope of this course, so we're not going to talk about these in this course. What we're going to look at are these three first here. So let's look at a simple requirement. This is what we have seen already. Here we have our template declaration. We have a concept declared. The concept name is TinyType. We're going to put in our requires clause. We're going to put in our parameter list, and we're going to put in our curly braces. Inside the requires clause, we have a statement here, which is going to enforce that size of t is less than 4. And what this really means, it's going to check that size of t, the syntax here is correct. And this can really throw people off. I have said this in the last lecture, but I set up this little example to really drive this home and show you that if you are not careful, your concepts are going to be really wrong. This is going to check for the syntax. So for example, if we call a function template with this concept with a car type, the concept is going to be satisfied, even if the size of a car is less than 4, obviously, but that's not going to be the job of this concept here. This concept is not going to enforce for the expression here to evaluate to true. It's going to just check the syntax. And if you pass something smaller than an int in a function template with this concept, this is going to be valid C++ syntax, so the concept is going to work. So now you must be asking, how can I enforce for the value of this expression to be true using concept? Well, for that, you will have to use nested requirements. And a nested requirement is going to have another requires keyword inserted in front of it. Now, if you use the syntax like this, now this is going to check that size of t is actually less than 4. If it's not less than 4, this is going to return false here, and the concept is going to fail. And this is how you can use nested requirements to enforce for some expressions to be true in your requires clause. Another kind of requirement you can set up for your concept is the compound requirement. And this is going to allow you to check if something doesn't throw an exception. You can do that using the no except keyword, but we're not going to use this now because this is not in scope for what we can do at this point in the course. But you can also check the return type of an expression and enforce that it satisfies some type trait, for example. So here we are saying for our concept, and if we pass in 2 parameters, the syntax for adding A and B must be correct and supported for those types. But the result of A and B must also be convertible to int. And you can do something like this. And this is going to work. You can enforce these kinds of things using compound requirements. Okay, now that you know about these kinds of requirements you can put in your requires clause, let's head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is zooming in on requires clause. We're going to grab our template files and we're going to put them in place. And we're going to open that in Visual Studio Code pretty quick by dragging and dropping here. This is going to open up our folder. We're going to do the usual. We're going to close the pane here. We're going to clean things up a little bit. And we're going to include our concepts library. Let's do that. We are going to set up a simple concept. We're going to say template, and we're going to say what the concept is. The concept is going to be called TinyType, and we're going to say what makes this concept a TinyType. We're going to put in our requires clause, and we're going to put in the template parameter, call it t, why not? And we're going to put in our closing semicolon here. Now, what is going to make this concept a TinyType is that the size of the template parameter here is going to be less than 4. Let's suppose we are doing a function and we want it to use for integral types that are smaller than 4 bytes in memory. Suppose you want to do this, and it is useful in the problem that you are trying to solve in C++. The way we can enforce this, we can say size of t is supposed to be less than 4. Let's say size of properly can't type can I. Okay, the moment we do this, you're going to see that this is valid C++ syntax, so we're not going to have any squiggly lines, but what you should know is that this is a simple requirement in C++ concepts. And what this is going to do, it's just going to enforce the syntax of what we do here. What we put here must be valid C++ syntax. So only enforces syntax. This is what you should really remember. Okay, now that we have this in, let's try it out and show you some problems you can really run into. We're going to set up two character variables. We're going to call the first one x. We're going to initialize this with 57. Why not? 67. And we're going to put in the other variable, which is going to be y, and it's going to have a 56n. You can put in whatever you want. Just make sure that you are within the range of a card type, which is between 0 and 255, if you remember. Okay, now that we have this n, I realize we don't have a function. We can try this on. Let's set up another function pretty quick. We're going to say tinytype auto. We can do that. You already know this syntax. And we're going to say add tinytype auto a and a tinytype auto b. We can do that. And we're going to return a plus b. Now that we have this, let's say a and b down here and call this function. We're going to say x and y. And we're going to try and compile this program. And it is going to compile fine because the type we are using to call the function, which is char, its size is going to be less than 4. Okay, so this is going to work and it is going to compile. Let's build with GCC. You're going to see that the build is good. Let's try and change the type here to int or even double. You know, double is 8 bytes in memory. So we expect this to probably give us something wrong. Double type is 8 bytes in memory. So we expect the size of t here to be false because the size of t is going to be 8 and 8 is not less than 4. This is going to be false. So some might expect this concept here to fail, but let's try and really prove you wrong. We're going to build with GCC and you see it's building successfully. What this is really doing is that with simple requirements like we have here, C++ is only going to enforce for this to be valid C++ syntax. And size of t is less than 4 is going to be valid C++ syntax even if this expression here evaluates to false. This is not going to enforce for the value of this expression to be false. You can't do that with simple requirements. What you will do is check that this is valid syntax. Now, what do we do if we really want to enforce that size of t should be less than 4? If you want that, you should use nested requirements. And the syntax to do that is really simple. We can go down here and put that in. We're going to say requires. We're going to add a requires keyword in front of this. Then we're going to put our expression here. Let's copy it and put it in. I don't want to type this again. The moment we do this, now compilation is going to fail if we pass a type whose size is not less than 4. And let's try and build again. You're going to see that the build is going to fail now, and we're going to have a failed concept. And you see build finished with errors. We have constraints not satisfied. And if we go down here, we're going to see required for the satisfaction of tinytype auto. And we passed in a double type whose size is 8 bytes in memory, and it is less than 4 bytes. You see the requirement here. It is not satisfied. We can do this using nested requirements. Okay, if we go down, for example, and change this to car, some people call this char, but I call this car. That's my habit. If we change this to car and try to build again, you're going to see that it is going to build fine because now, what is wrong here? Let's see what we got wrong. We are getting a compiler error here. What is the problem? It's going to say, let's go up and try to analyze this a little bit. It's saying deduce the return type does not satisfy placeholder constraints. And we are requiring for the return type of this guy to be tinytype. I think I know what the problem is. The problem is the arithmetic operations like the addition we're doing here are not supported for types which are smaller than int. Int is the smallest type we can use with arithmetic operations. So what the compiler is going to do is going to do implicit conversions from char to int. And inside here, what we will have are going to be int. The result of this is going to be int, and the return type is going to be deduced to be int. But int is going to violate the requirement we have here, which is saying that the size of tiny type here should be less than 4, and the return of int is not less than 4. So we can try and fix this by putting an equal sign here, and I think it's going to work. Let's do that and build again. This is a good learning experience. And now you see that the build is going to work because now the return type is going to satisfy our requirements. So let's prove that we are getting an int out of this actually. We're going to do auto result, and we're going to say equal and grab the result of this guy. We should really prove these things. And after this, we're going to print the result. We can do that. And we can even go further and print the size of result here. So we're going to say size of result. Okay, now that we have this in, we can build with GCC, and the build is good. Don't mind this squiggly line. It is probably Visual Studio Code messing with us. You see that the build is good. We can now bring up a terminal and run this and see the size of the return type and really prove that the compiler turned that into an int, even if we called our function with char arguments. This is interesting. So clear and run rooster. Now we're going to see result is going to be 123, and the size of the result is 4, even if we passed in char types as our arguments. Okay, so hopefully this proves that you can set up nested requirements to enforce for the expression here to be checked. Another type of requirement you can do is a compound requirement. Let's put this in, and we're going to put in a simple example to drive this home. I think I should take this function and put that below our concepts. So a compound requirement looks like this. You put your expression in a curly's like this, and then you can even put requirements on the values of the expression. For example, we can enforce that the value of a plus b here should be convertible to int. If it's not convertible to int, the concept here is going to fail. This is a compound requirement. You can even put no except keywords in here, but we're not going to go this far because we haven't really learned about exceptions. So for now, I'm going to take this out. I just wanted you to be aware that you can do that. Now that we have this concept in, let's play with it and see how we can make it break things. We're going to change our concept to addable. Let's say addable here, and we're going to say addable, and we're going to put in our char types here, and it is going to still work because we can add 2 char variables, and this is going to work because we can add 2 char variables, and this is valid syntax. What we're going to get out of that is going to be an int, because remember, the compiler is going to insert implicit conversions from char to int because it can't really add 2 char types. Int is the smallest thing you can do arithmetic operations on. So the result of this is going to be an int. So an int is convertible to an int. This is going to work. Let's build and show you that this is going to work. We're going to build this with the GCC. You see, build is good. We can try and run this and see what we get. After calling the function, we get result is 123, and this is going to be the size of 4 because we get an int out of this. Let's try and change this to double and see what we get. So double, let's say double here. And if we build, we expect this to work because adding up 2 doubles is going to give you a double. And we're going to return a double from this function, and a double is convertible to an int. So we're going to return a double from this guy, and this should say 8 now, because that's what we are returning from the function here. Let's build with GCC. You see, the build is good. We can clear and run rooster. This is going to say size of result is 8, because now what we are returning is going to be a double from this function here, and double satisfies our concept. Adding up 2 doubles is valid syntax, and what we get out of that is going to be a double, and a double is convertible to an int. This is going to work. Let's try and change our parameters here to string. We're going to comment out our x and y variables here, and we're going to set up 2 strings. We're going to say std string x, and we're going to say hello. And you know what we're going to say in y? We're going to say std string y, and we're going to say world. Why not? And the moment we do this, you see that we have a problem. Why do we have a problem? Because it is now a requirement for the result of A and B to be convertible to int. Remember that you can add up two strings. For example, you can say auto s and say x plus y. This is going to work because you can add up two strings and this is going to concatenate them. So this is valid syntax. Why are we failing here? Because we have a requirement for this to be convertible to an int, and the string isn't really convertible to an int, so this is going to fail. Let's build this program and show you that this is actually the case. We're going to see build finished with errors, and let's see the error we have. Okay, so constraints not satisfied. It's going to say required dissatisfaction of addable with auto here in requirement, and it's going to say A plus B does not satisfy the type requirement. Because what we get after adding A and B is not convertible to an int. And you see that here. A plus B convertible to an int, this is going to fail. Okay, so let's try and remove this requirement to convert to int and see that this actually works. We're going to remove this. I'm going to cut this out and try to build again. I am going to use GCC to build. And now you see that this is building because we no longer have the requirement of the return value of this expression, or result, I should say. The result of this function now doesn't have to be convertible to an int. Okay, let's put this back because I want you to see this later as a reference. And now you know how you can use compound requirements to really put constraints on your function templates. This is really all we set out to do in this lecture. I hope you found it interesting. I think I should comment out these guys because I don't like to leave you with code that has compiler errors. Let's turn this back to double so that this works. We're going to build again. Okay, the build is good. And we are going to stop here in this lecture. In the next one, we're going to see how we can combine concepts and do some crazy things. Go ahead and finish up here and meet me there.